June 8, 1944. Dawn breaks over Arromanches, France. 2 days after the bloodiest amphibious assault in history, engineers face an impossible deadline. The Allied invasion of Europe is already running behind schedule. Without a working harbor, the entire D-Day operation could collapse within weeks. But there's a problem. The nearest usable port is in German hands, 40 miles away. What happens next defies logic. In just 6 days, military engineers will construct the largest artificial harbor ever created, using 2 million tons of floating concrete, positioned while under enemy fire, in one of the most unpredictable seas in the world. This isn't about who won the battle. This is about how they solved an engineering problem that military experts said was impossible.
Let's rewind 18 months to understand why the Allies needed to build a harbor from scratch. August 19, 1942. Operation Jubilee, the British-Canadian raid on Dieppe, ends in catastrophe. Of the 6,000 troops who landed on French beaches that morning, 3,600 are dead or captured. 30 tanks destroyed, 106 aircraft shot down. The assault never even reached the town itself. Naval Commander John Hughes Hallett rides back across the English Channel on his vessel that afternoon. He's just witnessed a massacre. Every military doctrine says you need to capture a port to supply an invasion force. But Dieppe proved something chilling. The Germans had turned every French harbor into a fortress. Concrete bunkers, artillery positions, machine gun nests covering every approach. According to witness accounts from combined operations records, Hughes Hallett turns to a fellow officer and says, "If we can't capture a port, we'll have to take one with us." The statement sounds absurd. Ports take years to build. They require deep water foundations, massive breakwaters, crane systems, piers extending hundreds of feet into the ocean. How do you take a harbor anywhere? But Churchill sees genius in the idea. On May 30, 1942, 3 months before Dieppe, he'd already circulated a secret memo titled Piers for Use on Beaches. He wrote, "They must float up and down with the tide. The anchor problem must be answered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." Here's the scale of the challenge the planners faced. The proposed invasion of Normandy would put 150,000 troops ashore on D-Day. But that's just the beginning. To break through Hitler's Atlantic Wall and push into occupied Europe, the Allies would need 2 million more soldiers, 500,000 vehicles, and 4 million tons of supplies within the first 100 days. Every single ton would need to come through a harbor. The Normandy coast has no natural harbors. The nearest port, Cherbourg, sits 30 miles west, fortified with German troops who would destroy the facilities before surrendering. Intelligence reports estimate it would take months to repair after capture. The arithmetic is brutal. Without harbor facilities, the invasion would stall. Supplies would pile up on open beaches. Vehicles would bog down in sand. Reinforcements couldn't reach the front lines. The Germans would counterattack a stranded army. Military planners calculate they need harbor capacity to handle 12,000 tons of cargo and 2,500 vehicles every single day. Not in calm weather, in all conditions. Atlantic storms, 26-foot tides, waves that can flip landing craft like toys. And they need it operational within 3 weeks of landing. This is the problem handed to a committee of civil engineers in August 1943, just 10 months before the invasion. The chairman is Colin R. White. The location for the first meeting? The Institution of Civil Engineers in London. Not a military command center, a civilian engineering society. White's team faces technical challenges that would make most engineers walk away. The harbor must be built in Britain, disassembled into pieces, towed across 60 miles of open ocean, then reassembled on enemy beaches while under artillery fire. Every component must float for transport, but sink on command to create stable foundations. Oh, and one more thing. The entire project is classified top secret. The 200,000 workers building the components can't know what they're making.
The solution the engineers develop is called Mulberry. 2 complete artificial harbors, each the size of Dover. Let me break down how this works, because the design is brilliant. Think of a natural harbor. You need 3 things: a breakwater to stop waves, piers for ships to dock, and roadways to move cargo ashore. The Mulberry team had to create all 3 from scratch, using materials that could survive a 60-mile ocean crossing. First, the breakwater. This is your first line of defense against the Atlantic. The team considers crazy ideas, including creating a wall of air bubbles released from underwater pipes. But physics kills that plan fast. Instead, they design 3 layers of protection. The outer ring, floating steel breakwaters called bombardons. Each unit measures 200 feet long and 25 feet high. Made of steel and rubberized canvas shaped like giant plus signs. 24 units linked together create a mile-long wave barrier. The middle ring, scuttled ships codenamed corncobs. The Royal Navy assembles 61 vessels, old freighters, obsolete warships, including the 1911 French battleship Courbet. These ships will sail to Normandy under their own power, position themselves in precise formations, then deliberately flood and sink to create permanent breakwaters. The inner ring, Phoenix caissons. This is where engineering becomes art. Phoenix caissons are hollow concrete boxes, the largest structures weighing 6,000 tons, standing 60 feet tall, 200 feet long. They're essentially floating buildings. Each one contains multiple chambers that can be flooded to sink it or pumped dry to float it. Here's the ingenious part. The Phoenix units are built at shipyards across Britain, floated into position, then intentionally sunk off the English coast before D-Day. This hides them from German reconnaissance aircraft. When needed, they'll be refloated by pumping out the chambers, towed to France, then sunk again in precise positions to form the harbor breakwater. But there's a critical problem discovered during testing. A Phoenix caisson runs aground near Southampton. Engineers try to refloat it using the standard pumps, designed for moving sewage horizontally through pipes. The pumps can't generate enough vertical lift to raise water 60 feet up and out of the chambers. The mission nearly fails before it starts. Enter Captain Edward Ellsberg, a U.S. Navy salvage expert. He reviews the British plans and delivers a blunt assessment. The refloating technique won't work. Churchill himself intervenes, removes the task from the Royal Engineers, hands it to the Royal Navy. Ellsberg locates every salvage barge in Britain, assembles heavy-duty pumps capable of vertical lift, and redesigns the entire refloating operation. This one fix saves the invasion. Now for the piers. These need to handle 2,000-ton cargo ships in waters where the tide rises and falls 26 feet twice daily. Static piers won't work. They'd be underwater half the time. Major Alan Beckett of the Royal Engineers designs the solution. Floating pierheads codenamed spuds. Each consists of a steel pontoon with 4 massive legs. The legs rest on the seabed while the pier floats freely, rising and falling with the tide. Ships can dock it any hour. Connecting the spuds to shore are floating roadways called whales, bridge segments mounted on pontoons called beetles. Each whale segment spans 80 feet. The segments are linked by flexible joints that twist and bend with wave action without breaking. But what holds everything in place against current and storm? Alan Beckett invents a new anchor called the kite. Traditional ship anchors rely on weight. The kite anchor uses a specialized blade design that digs deeper into the seabed the harder you pull. The holding power is so extreme that after the war, most kite anchors couldn't be recovered. They're still buried in the ocean floor off Normandy.
The Royal Navy doesn't believe Beckett's claims about holding power. They refuse to use kite anchors for the Bombardon floating breakwaters. This decision will prove catastrophic.
September 4th, 1943. The combined Chiefs of Staff issue the order: begin construction immediately. The Mulberry Harbors must be ready by May 1st, 1944. That's 8 months to build 2 complete artificial harbors from scratch. 200,000 workers mobilize at sites across Britain: London, Tilbury, Woolwich, Southampton, Portsmouth, Middlesbrough. The operation requires 147 Phoenix caissons alone. Each one needs more than 6,000 tons of reinforced concrete and 350 tons of steel rebar. Total materials for both Mulberries: 2 million tons of concrete and steel, more construction than many countries complete in a decade. Major construction firms bid for contracts: Balfour Beatty, Costain, John Lang, Taylor Woodrow. 27 contractors build Phoenix caissons at 35 different locations simultaneously. Hundreds of smaller companies fabricate whales, beetles, spuds, and anchoring systems. Security is absolute. Workers receive component specifications without context. Welders build steel frames. Concrete crews pour caissons. Nobody knows they're creating a harbor. Rumors spread that the massive concrete structures are post-war building materials or floating fuel tanks. A senior officer from Whitehall visits construction sites to reassure workers their labor is vital for the war effort without revealing what they're building. German intelligence photographs British ports. They spot the concrete structures. Lord Haw Haw, the Nazi propaganda broadcaster, taunts British radio listeners in May 1944. "We know what you're doing with those caissons. You intend to sink them off the coast when the attack takes place. Well, chaps, we've decided to help you. We'll save you trouble and sink the caissons before you arrive." The Germans believe the structures are fuel storage tanks. They completely miss the true purpose. Meanwhile, the construction deadline is crushing. Despite employing tens of thousands of laborers, the work barely finishes on time. Phoenix caissons require launching basins, huge excavations carved into riverbanks along the Thames and Medway. Each caisson must be built, floated out, sunk in designated holding areas, then refloated when needed. The Royal Navy assembles 200 tugboats for towing operations. Each tug receives a large M painted on its funnel. Tug crews take fierce pride in the designation. They know they're part of something historic, even if they don't know what. Coordinating the logistics is a nightmare. Each Phoenix caisson needs 2 tugs for the cross-channel journey. Bombardons must be assembled in sequence. Whale roadway segments need precise manufacturing tolerances or they won't link together. Spud pier heads require hydraulic systems that can lift and lower with mechanical precision. One miscalculation, one failed component, and the entire operation collapses. Testing reveals problems. A trial assembly in Wigtown Bay, Scotland, chosen because its tides match Normandy, exposes weaknesses in early designs. During a storm, some pontoon sections wash away. Floating roadways collapse under 7-ton truck weight. Engineers redesign on the fly. By June 1, 1944, the components are ready. Thousands of sections wait at assembly points: Portland, Poole, Plymouth, Selsey, Dungeness. Some sites are within range of German long-range artillery at Calais, a deliberate deception to make the Germans believe the invasion will target that region. Then the weather turns. June 4th, Eisenhower postpones the invasion by 24 hours due to storms. The Mulberry components sit exposed, swaying in the wind. Engineers worry the structures will break apart before they even cross the channel. June 5th, Eisenhower gives the final order. Operation Overlord begins at dawn tomorrow. The Mulberry Convoy
prepares to sail.
June 6, 1944, 12:30 p.m. While American troops are still fighting their way off Omaha Beach, the first Mulberry convoy appears on the horizon. 45 block ships, the corn cobs, arrive first. These obsolete vessels steam into position under their own power. Engineers aboard each ship follow precise coordinates. They open sea valves, flooding compartments. Within hours, 61 ships have been deliberately sunk in two arcing lines off Omaha and Arromanches beaches. The scuttled ships create instant sheltered water, the gooseberries. Landing craft can now unload behind the protection of the hulks while construction continues. June 7th, the Phoenix convoys begin arriving. Each convoy consists of 8 Phoenix caissons, 8 bombardons, 4 pierheads, 10 whale roadways, and support vessels. Towed by the tug fleet at 4.5 knots, faster than the planned 3.5 knots, to reduce turnaround time. Planners expected to lose 20 to 25% of the components during the crossing. Actual losses? Less than 5%. Half a floating roadway sinks. 1 caisson runs aground. Otherwise, the massive structure survives 60 miles of open ocean. Now comes the hardest part: assembly under fire. German artillery on the bluffs above the beaches can still reach the construction zones. Luftwaffe bombers attempt night raids. Engineers work around the clock, positioning multi-thousand-ton concrete structures with precision measured in feet, not yards. The first Phoenix must be sunk at dawn on June 8th at Arromanches. The operation requires perfect timing. Tugs position the caisson. Engineers open flood valves. The Phoenix settles, but slowly, too slowly. The tide turns mid-sink, swinging the massive structure at right angles to its planned position. Disaster? No. The misplaced Phoenix creates an accidental windbreak from the west that improves the harbor design. At Omaha Beach, positioning goes faster. American engineers sink the first Phoenix at the correct spot. By June 11th, just 5 days after D-Day, the Gooseberry breakwaters are complete. Phoenix caissons are being positioned at a rate of 15 per day. By June 15th, 2 piers and 4 pier heads are operational at Omaha. British engineers at Arromanches have sunk 115 Phoenix caissons in a 5-mile arc from Tracy-sur-Mer to Eisenhower. The harbor encloses 2 square miles, the same size as Dover. Anti-aircraft guns are mounted on the Phoenix superstructures and block ship hulls. The 397th and 481st Anti-Aircraft Artillery Battalions take positions on the concrete structures, creating floating defense platforms. From June 15th to 18th, Mulberry A at Omaha lands 18,938 troops daily. Mulberry B at Arromanches lands 15,774 troops per day. Both harbors are moving 2,000 vehicles and 25,000 tons of stores every 24 hours. The impossible has been achieved. 2 fully functional artificial harbors built in 6 days. Then nature intervenes.
June 18th, 1944. Evening. The weather at Omaha Beach is perfect. Calm seas, clear skies. American Mulberry A has just officially opened for operations. Supply ships line up to dock at the piers. At midnight, the barometer begins to fall. By 3 a.m. on June 19th, wind speeds hit 30 knots. 8-foot breakers roll in from the northeast. This is the worst channel storm in 40 years. For 72 hours, the artificial harbors battle forces they were never designed to withstand. The mulberries were engineered for summer conditions,
Moderate winds, manageable swells. This is a winter gale in June. The Bombardon floating breakwaters are rated for winds up to 30 knots. The storm exceeds that within hours. The Bombardons, anchored with traditional ship anchors instead of Beckett's kite anchors, begin tearing loose. Without kite anchors digging deeper under stress, the Bombardons drift. Several Bombardons break their moorings and crash into the Phoenix caissons. Concrete cracks under the impact. Water floods the internal chambers. Phoenix units designed to be sunk in controlled conditions are now failing catastrophically. At Arromanches, Lieutenant Colonel Raymond May orders emergency procedures. Moorings are doubled. Ships outside the harbor move to deeper water. 500 landing craft shelter inside Mulberry B behind the Phoenix line. Royal Engineer bridge parties work 40-hour shifts without sleep. They're fighting to save piers as waves wash over pontoons. Whale roadway segments twist under the force. Anchors drag. British tugboat crews battle to corral landing craft that have broken loose and are smashing into the harbor structures. But the British harbor holds. Barely. At Omaha, Mulberry A is being destroyed. The American harbor faces larger waves. Scientific analysis later confirms the wave height at Omaha exceeded what struck Arromanches. Combined with the American decision to assemble the harbor on a faster timeline, meaning some Phoenix caissons weren't as securely anchored, the structures fail. 21 of the 28 Phoenix caissons are completely destroyed by a combination of wave action, scouring of the seabed foundations, internal water pressure from flooding, and bombardons smashing into them. The piers collapse, roadways wash away. By June 22nd, when the storm finally dies, Mulberry A is gone. General Omar Bradley walks the beach at first light on June 23rd. He later writes, "I was appalled by the desolation, for it vastly exceeded that on D-Day. Landing craft are stacked 3 deep on the sand, broken equipment everywhere, vehicles crushed under collapsed pier segments. The scene looks like the aftermath of a battle, except the enemy was weather." At Arromanches, Lieutenant Colonel Raymond May walks the Mulberry B piers at dawn, saluting the exhausted engineers who greet him. He says nothing, but they understand. They've saved the harbor. Damage assessment? 6 Phoenix caissons lost. Piers damaged but repairable. The breakwater held. Even during the worst day of the storm, British engineers managed to offload 800 tons of supplies through Port Winston, the nickname for Mulberry B. Over the 4-day storm, 7,000 tons of stores passed through the battered harbor.
The engineers make a crucial decision. Mulberry A at Omaha is beyond repair, but its components aren't scrap. Salvage crews pull usable Phoenix caissons, whale sections, and pier equipment from the wreckage. Everything that can float is towed to Arromanches. Mulberry B gets reinforced with American components. Engineers had specially strengthened caissons to the breakwater. The harbor that was designed to last 90 days will operate for 10 months. The logistics are staggering. At peak efficiency, Port Winston handles 40,000 tons per day. That's 20,000 jeeps, 800 tanks, or 40 million rifle rounds every 24 hours. By October 1944, when the Allied armies have broken out of Normandy and are advancing across France, Port Winston has landed 2.5 million soldiers, 500,000 vehicles, 4 million tons of supplies. 25% of all Allied supplies reach France through Arromanches, 15% of vehicles, 20% of reinforcements. This one harbor, built in 6 days, battered by storms, operating far beyond its design life, becomes the logistical backbone of the liberation of Western Europe.
At Omaha Beach, American forces adapt. Without functioning piers, they land supplies directly onto the beach using the gooseberry breakwater for shelter. DUKW's amphibious cargo carriers shuttle between ships and shore. Smaller ports at Port-en-Bessin and Ouistreham supplement capacity. By November 1944, the Allies captured the port of Antwerp. Finally, they have a deep-water harbor with permanent facilities. Port Winston is officially decommissioned on November 19, 1944. The Royal Engineers dismantle what they can. Whale bridge segments are salvaged and reused. Some are shipped to repair bombed bridges across France, Belgium, and the Netherlands. Others go to Cameroon in 1954 to build infrastructure. In the 1960s, 3 whale segments are repurposed at Fort Dagenham in England. Cars roll off the assembly line directly onto ships using D-Day harbor components. But the Phoenix caissons? They stay. Too massive to move, most remain exactly where they were sunk 80 years ago.
Today, you can walk the beach at Arromanches and see the remains of Mulberry Bee offshore. Dozens of Phoenix caissons still break the waves, exactly as they did in June 1944. General Eisenhower called Mulberry one of the most inventive logistical undertakings of the war. General Bradley described it as engineering brilliance that saved the invasion. Albert Speer, Hitler's armaments minister, admitted after the war that the Mulberry Harbors made Germany's Atlantic Wall irrelevant. The Nazis built thousands of bunkers, planted millions of mines, fortified every port, all based on the assumption the Allies would need to capture harbor facilities. Instead, the Allies brought their own harbor. The engineering lessons resonate today. The Phoenix caissons pioneered techniques now used in offshore oil platforms. Massive floating structures that can be positioned precisely and sunk to create stable foundations. Modern artificial islands in Dubai and Singapore use evolved versions of Mulberry technology. The whale pontoon bridges introduced flexible roadway design, segments that move independently but function as a whole. Modern military mobile bridges trace their lineage directly to Alan Beckett's D-Day design. And the kite anchor? Still considered one of the most effective deep-holding anchor designs ever invented. The anchors that held Port Winston through the June storm demonstrated holding power that modern marine engineers still study. But perhaps the most important lesson is this: the Mulberry Harbors succeeded because engineers were given an impossible problem and refused to accept no as an answer. 200,000 workers built components they didn't understand. Tugboat crews towed structures across 60 miles of hostile water. Royal engineers assembled a harbor while under enemy fire. And when a 72-hour storm destroyed half of the project, they rebuilt it with salvaged parts and kept going. The Mulberry Harbors weren't perfect. Mulberry A was destroyed. Components failed. Designs needed mid-operation fixes. But they worked long enough and well enough to change history. 6 days to build a harbor, 10 months of continuous operation, 2.5 million soldiers landed, 4 million tons of supplies delivered, all from floating concrete and engineering brilliance.
If you found this story as incredible as I did, you need to subscribe. This channel specializes in military engineering problems that change the outcome of wars, not the battles themselves, but the technical solutions that made victory possible. Next video, we're looking at how Allied codebreakers at Bletchley Park built a machine to crack German Enigma messages and the mathematical breakthrough that made it work. Hit subscribe, turn on notifications, and check out the video on screen now about the engineering disaster that nearly stopped D-Day before it started. Thanks for watching.